All right, with normalization and orthogonality, this is a good time to talk about an orthonormal basis. An orthonormal basis is just building blocks for any element in your vector or function space that are mutually orthogonal. X hat, y hat, and z hat fit the bill. They're mutually orthogonal and are normalized. And x hat, y hat, and z hat fit the bill there too. X hat and y hat and z hat, they're normalized and they are mutually orthogonal. They form, it turns out, an orthonormal basis in three-dimensional vector space. What that means is you can build any three-dimensional vector out of combinations of x hat, y hat, and z hat just by mixing in appropriate amounts. A sub x tells you the amount of vector A that's in the x hat direction. A sub y tells you the amount of vector A that's in the y hat direction, and so on. If we use this more abstract notation and represent x hat, y hat, and z hat as just unit vectors E sub n, where n could take on 1, 2, or 3, 1 would represent x, 2 would represent y, 3 would represent z, we could rewrite this, kind of cute, as this sum. So when n is 1, we'd have A1, E sub n hat 1, well, that's A sub x, x hat. When n is 2, we'd have A sub 2, E sub n 2, well that'd be A sub y, E sub y hat, and so forth. So we run the sum from 1 to 3 and we pick up all these terms. So this is a nice compact way to write this, which normally we wouldn't bother with, but we want to do this because I want to draw analogies to our other quantum situations. All right, finally what I want to say before we move to our other systems, A sub x can be thought of as the projection of the vector A onto the x direction, or even the projection of vector A onto the x hat unit vector. I could write that this way. A sub x is in fact the dot product of x hat and A, so this can be thought of as a way of representing the projection of some vector onto one of its basis vectors. That is, the projection of a vector onto one of its basis vectors can be represented as a dot product, which is a special case of an inner product. So maybe we can do a similar thing with these other systems, and we'll see that. Okay, so to summarize what I said here, x hat, y hat, and z hat form an orthonormal basis for vectors in 3 space. That is, we can build any three-dimensional vector out of linear combinations of these. Well, it turns out that the analogous animals in our infinite square well function space, an analogous role is played by eigenfunctions of the infinite square well Hamiltonian. So that is, if we find our, we get our Hamiltonian operator, we find the eigenfunctions of the Hamiltonian. These are the special allowed states with, special energies. These eigenfunctions can be used to build any possible state that could be in the infinite square well. So if we represent the state capital Psi to be an arbitrary quantum wave function in our infinite square well problem, we can build any possible function with some linear combination of these special states, the eigenstates of the Hamiltonian. That's fantastic. We'll get to how you could figure out these coefficients in just a moment. Abstracting this, we can just talk about any quantum system. We can build our overall quantum state with linear combinations of eigenstates of the Hamiltonian. So I could represent eigenstates of the Hamiltonian operator in some abstract form like this with part of a bracket. And then we can build any abstract quantum state that could be in our appropriate state space for our quantum mechanical problem out of these eigenstates of the Hamiltonian. All right, so how do we figure out these little c sub n's, these little coefficients? Well, these are analogous to this. which just is an abstract way of representing the components, a sub x, a sub y, a sub z. What were these components? A sub x is the projection of vector A onto x hat, which is equal to the inner product of x hat and vector A. So let's generalize that, or let's take that same machinery. C sub n should be the inner product, well, should be the projection of our state psi onto the corresponding building blocks. We write that as an inner product of psi sub n and big psi like this. So this is analogous to this, and this is analogous to this or that. So here I've taken the inner product of the building block with the function that I'm trying to build, integrate over the range of the problem. That's our C sub n. This is just an inner product in the same way that this is an inner product. And I've written it totally analogously. Abstracting that to our, abstract quantum Dirac notation, C sub n is just the inner product of the building block psi sub n with the overall state you're trying to build. That is, C sub n is the projection of capital psi onto little psi sub n. Very good. All right, so these eigenstates of the Hamiltonian, or in infinite square well function space, the eigenfunctions of the Hamiltonian can be building blocks to build any appropriate quantum wave function or quantum state, and analogously to the way that x hat, y hat, and z hat can be used to build any three-dimensional vector in three-dimensional vector space. Okay, we have a few more analogies to draw. It turns out that, and this is a very important aspect of quantum mechanics, that if you've expanded some quantum state in terms of eigenstates of the Hamiltonian, or if you've expanded some wave function in terms of the eigenfunctions of the Hamiltonian, that the expansion coefficients, the C sub n's, relate to probabilities of obtaining particular energy results. So remember, these eigenfunctions of the Hamiltonian have corresponding energies. There's some energy E sub n corresponding to the state psi sub n. All right, so to get those probabilities, what you do is you take the complex square of these coefficients. The complex square is take the complex conjugate of C sub n multiplied by C sub n. That gives you the probability of obtaining the corresponding E sub n if you were to measure the energy. Now, naturally, an extension of that, a consequence of that is if this is the probability of one corresponding outcome, if you add up all the probabilities for all the outcomes, you better get a probability of 1. If you measure the energy, you're going to get an energy value. So if you add up all the possible probabilities for all the possible outcomes, those should come out to 1. So that's conservation of probability. Great. Now, is there something analogous to this in three-dimensional space, in three-dimensional vector space? Yes, there is. If we take a sub x, square it, take y sub x, square it, take z sub x, a sub z, and square it, and add them all up, you get the square of the magnitude of the vector A. So a sub x squared plus a sub y squared plus a sub z squared is the same thing, mathematically, as c1 squared plus c2 absolute squared plus c3 absolute squared, and so on. Add them all up, you get 1. Well, here you get 1. Here you get the magnitude of A. So, but there is an analogy. In quantum mechanical problems, we have conservation of probability. In three-dimensional vector space, we have the Pythagorean theorem. Now, so you might wonder why these things are squared. Well, the squarage comes from having something that's conserved. In our three-dimensional ordinary vector space system, if I just take a sub x plus a sub y plus a sub z without the squared, I don't have anything. I just have some number that doesn't mean anything in general. I need to square these things to get something else that means something. Well, so it shouldn't be so surprising then that to get something meaningful in quantum mechanics, you need to square these things to get, for example, conservation of probability. All right, finally, one last comment. The interpretation of the absolute squares of C sub n as being probabilities for corresponding energies, if we were to make an energy measurement, gives us a shorthand way to write the expectation value of the energy, which we can write this way. The Hamiltonian operator in brackets is the expectation value of the energy. We can just write that as a probability weighted sum of all the possible results. So if I have some results, each result, if I multiply it by the probability of getting that result and add them all up, I'll get the overall value. So this expectation value of the energy is a probability weighted average of all the possible energy results. So this is just a straightforward mathematical consequence of this interpretation. All right, so there's a lot of material here, but hopefully the goal is not to try and cause confusion, but to use things we know about ordinary three-dimensional vectors to help us get a better grasp of some of the mathematical machinery that's going on with quantum mechanical problems such as the infinite square well. Sometimes the details are complex. We've got all these integrals, but if we can recognize that the role that inner products play in all of this and realize that inner products are just a mathematical extension of good old dot products in ordinary three-dimensional vector space, if we can understand the underlying abstract mathematics, sometimes that gives us a tool for better representing or better understanding what's going on with the quantum mechanical machinery. Thank you.